So yesterday, the first examples we looked at for 6.1 were more biology, population. And what's interesting is the two most common applications of exponential functions are biology and business. So today we're going to look at some business applications. And then we'll look at one other scientific application. So the formula you need to write down for this section is the compound interest formula. Now, the thing we really need to talk about is what do each of those letters stand for, okay? So let's just go over what those will stand for. So if you look at this formula, it looks pretty similar to the one we had yesterday, except the one we had yesterday, if you take out the n, because the one we had yesterday was like a yearly sort of growth. This formula works for different type of accounts depending on how the account is worded. So if you go to a bank, most banks give interest rates monthly. So what this N stands for is how many times in a year does a month occur, or how many times in a year are they willing to give you interest. So if they say monthly, so the N is the number of compounding periods per year, that would be 12. If they say biannually, that's twice a year. If they say quarterly, that's 4 times a year. So they're going to give you language as to how often it happens. If it says annually, that's where the 1 occurs. This would be 1. So this formula is actually a version of the other. It just allows us to account for the way that a bank could possibly give you money. So what you want to know is that the A sub T stands for the final amount that's in your account. The P is our starting investment. Yesterday we learned that the P was our starting amount even in biology. In a money account, same idea. That's what that P is going to be. The R is our annual interest rate. You do want to make that the decimal form. And so if it says 5%, move that decimal place 2 places to the left or divide by 100 to find the correct decimal that you want to use in your account. And then again, N is that number of compounding periods each year. So if it says monthly, use 12. If it says biannually, 2, and so on. And then T will be how many years are you going to keep your money in the account. Now, this formula is used usually 2 ways. If you have a savings account and you start with something, it will do it. If you have a mortgage, like a loan for a car or a house, they may calculate this to see what you owe in total, and then they'll break it down by how many payments you might have. So they'll calculate that total. If it's a 3-year loan and your interest rate is blank, and they would cut that down into your equal number of payments. So let's take a look at an example. Let's do one. So it says if we want to invest $3,000 in an account paying 3% interest compounded quarterly, how much is in the account after 10 years? So the first thing I want to do is I want to write down the formula, and then I want to break down each piece and how we pull that from the word problem. So let's write down our formula. So it is A sub T, or A of T, is P times the quantity of 1 plus R over N times, or to the power of NT. So P times the quantity of 1 plus R over N to the power of NT. Now you're going to need to know that formula, and you're going to need to know what each one of those things stands for. Okay, so the P is our starting amount. In this case, it says that we want to invest $3,000. So that's our starting amount. The rate is 3%. So our rate is 3%, but in the formula, we want to use the decimal equivalent to 3%, so 0.03. These words here, compounded quarterly. There are 4 quarters in a football game. There's 4 quarters in $1. So anytime you see quarterly, that should bring up in your brain the number 4. And so the N is how many times per year are they going to calculate the interest? And that would be 4. And then the last thing that we need for us to use this formula properly is how long are we going to keep this particular account? How long are we going to keep that money in the account? Or if it was a loan, how long are we going to keep the loan? And so this would be 10 years. Okay, so now we have all of the stuff, and it should be hopefully just a plop the stuff into the formula. So I'm just going to replace everything and then we'll talk about it. I'm sorry, my N is 4. How about if I put the 4 in the right spot? Okay, so let's just kind of break this down for a minute. So here's my starting amount, 3,000. Here is my interest rate, which I've written as a decimal. Here is how many times per year they're giving me interest, 4 times. And then the T is there. And this T, you know, a lot of times, sometimes they'll just say A of, but they'll say A instead of A of T. But this just tells us this is how much is in the account after 10 years. Okay. Now, here's my suggestion when you're doing this problem so you don't mess up entering into a calculator. Let's get a number inside of the parentheses. Let's get a power as a whole power. So 4 times 10, you can do that in your head. That's 40. Now, 1 plus 0.03 divided by 4 is a long decimal. When all possible, you want to keep that decimal out, however many places the calculator says, or whatever's on the screen. You know, even if it fills up the screen, you want to be as accurate as possible. Don't round until the end of the problem. If you had a bank account, they would not round until the end of the problem most of the time. Now, just like we had looked at those exponential problems yesterday, I always told you do this first. So into the calculator, I would probably put that 1.0075 to the 40th power, hit equals, get an answer. Now, I'm just going to show you what my calculator reads. I am not going to clear it out. I'm just showing you that my calculator reads a really large number. Long number, not a large number necessarily. And then I'm not going to clear my calculator out. I'm just going to hit times 3,000. And then this is money. So we know how many decimal places naturally we should go to. We should go to 2 decimal places to the nearest penny. So we would have $4,045.05 in the account. Okay, so let's just go over it one more time. R is our rate. N is how many times per year they're going to give us interest. P is our starting amount. T is our years. Do inside the parenthesis first, then take that parenthesis to whatever power you're using, hit equals, get that number, then hit times 3,000. Does that make sense how that works? Okay. Because it's a monetary thing, go to the nearest penny. If you know, we saw the biology ones yesterday. If it's to the nearest deer, we don't want to say it. We have 0.5 deer. That's weird. So round to that nearest whole number. So for biology things, real life things, round to the nearest whole number. For money, round to the nearest penny. Okay? Okay. Everybody got that? Maybe? Yes.
What do you do with the 8 times 10?
What times 10 did you tell me? Which part?
8 times 10.
This is a function A. This is the function A where I plugged in 10. You can just call it A. Don't let it confuse you. It's just saying I am using the function at 10. Yeah, that's just a notation thing. That is just the amount in my account after 10 years. So it's not times 10. It's not anything. This is just more of a function notation. Any other questions? Okay, let's look at another one. It says, after 18 years, an account now has $40,000 in it. The account earned 6% interest compounded semi-annually. How much was initially invested? So I'm going to write it down, and I'm just going to leave it in A because I don't want that to confuse you. So let's write our formula like that. So let's remember what each of the variables stands for. The A is our final amount. They told us our final amount was $40,000. Our P is our starting amount. That's what they ask for when they say how much was initially invested. Our R is our percentage rate written as a decimal. So our N is the number of times per year they are saying we have, they're going to give us interest. So take a look at this word right here. Semi-annually. Sometimes you'll even hear that word used when it comes to shopping and sales. It's our semi-annual sale. Semi-annual just means twice a year. So our N is 2. Twice a year, they give us interest. So once we have all of our things, oh, we do need T. T is 18. Okay, 18 years. Once we have all of our variables, now we are ready to plop everything in. Okay, so let's take a look. Our A is 40,000. Don't know the P. That's what we're going to be looking for. 1 plus our R is 0.06. Our N is 2. And then this is 2 times a time of 18. Now, what I want to do is I want to get this as accurate as possible first, okay? So 1 plus 0.06 divided by 2, if you enter that into a calculator, 0.06 divided by 2 is 0.03. So that's 1.03. Get that number. Get 2 times 18. 2 times 18 is 36. Now, I would not at this point do anything with that. Let's just think about the fact that this is going to be a number on my calculator, right? It's just a number. And if it is by the P like that, what does it indicate that the P and that number are doing to one another mathematically? Adding, subtracting, multiplying, or dividing? Multiplying, right? What's the opposite of that? So we have to divide both sides by that thing. Now, I'm just going to write it as that thing because I don't know what that thing is right at the moment. The calculator is going to tell me what that thing is, okay? But I need to divide it off so I can cancel it, okay? So my amount in my account is going to be 40,000 divided by that thing. Now, this is where we'll put it all into a calculator, okay? So if I enter into the calculator 40,000, and again, this is kind of like that same idea, don't round till the end. That's the kind of the idea I'm going with. So let's put my 40,000 in. I'm going to hit divided by 1.03 to a power of 36. And then I'm going to round that to at the end. I'm going to round that at the end. So the starting amount in the account, rounded to the nearest penny, is $13,801.30. So my key here, one thing to take away from it, be as accurate as possible. Don't round till the end. And then if it's money, round it to the nearest penny. So you're going to have to use your rules of algebra to solve some of these equations. Some of them you're just plugging in, getting your number. This one, because we were missing that P, we had a little bit more work to do. So there is example 7. Are there any questions about example 7? Okay. Now, there are biology applications. There are monetary business applications. This formula here is an interesting one. It is something called continuous growth and decay. I'll just sometimes call it the PERT formula. It almost looks like you're trying to spell the word PERT. Or there used to be a shampoo called PERT. I don't know if it still exists, but anyway, this is the PERT formula, I call it. It is P, that same initial starting amount, but your that 1 plus r to the n is kind of gone, and the number e pops in, and that is e to a power of rt. All the things in the formula are still the same. A is your final amount, P is your starting amount, R is your rate, T is your time. But what's interesting about this, if R is positive, it is a growth rate. You're going to see that mostly in biology applications. This decay one, you see not only in biology applications, like say you have a petri dish of bacteria and you add an antibiotic to it, it's going to start decaying at some kind of rate. If the R is negative, we get a decay. So that happens sometimes in populations of some sort, biology, but it also happens in scientific applications of like something that is decaying, like carbon decay, uranium, or some type of radioactive something, that radioactive decay. So this formula shows up in lots of weird places that E pops in. Just like in circles, pi shows up a lot. In this PERT formula, E shows up in lots of weird places. So let's look at a business application with an E in it, and then let's look at it's more of a physical science problem. Okay, so anyway, if you see a problem and it lists this compounded continuously, if you see the words compounded continuously, that tells me that I need to use the PERT formula. So if it says compounded continuously, that is your main key. Hey, I better use the PERT formula, okay? So that, first off, know that language. Now, if they say monthly, once a year, annually, semi-annually, that's the other formula. But if they use the word compounded continuously, this is the formula we want, okay? Now let's pull out from the problems everything they told us. We are investing $1,000, so that's our starting amount. Our interest rate is 10% per year. Write that as a decimal, 0.10. How much is in the account after 1 year? Our time is 1. What's nice about these problems is that we have actually a few less variables to worry about. So we are looking for how much after that time, so that's our A. So let's plop everything into the formula. So we're looking for A. P is 1,000. And then we have E to a 0.10 times 1. So I tend to do this, whether you do it in your head or in a calculator, before I put it in my calculator. So that's 1,000 E to the 0.10 power. Okay. Now, at this point, hopefully you found the E button on your calculator. On the calculators in the back of my room, just look for that LN button, and then you'll see the little E above there, and you have to hit the second first for the E to appear. And if we do 1,000 times E to a power of 0.10, rounded to the nearest penny, because this is money, this is $1,105.17. Okay, so $1,105.17. Now, if they asked you how much interest did you gain, we had 1,000 to start with. We now have $1,105.17. That means the interest that they put in the account was that $105.17 extra. Okay, so those are some applications that you're going to see. There's one more I want to do. I believe that's the last one. Yep. And that is a more scientific application. And it has to do with like radioactive decay. So it says radon-222 decays 17.3% per day. If we start with 100 milligrams, how much is left after 3 days? So we're going to assume that this is a continuous decay. We're going to assume this is a PERT formula. Most applications with biology or like a physical science will use that PERT formula. Okay, now what do we know? It says if we start with 100 milligrams, how much is left after 3 days? So our starting amount is 100 milligrams. So that's our P. Now our rate, here's something you don't want to forget. It is a decay. That decay tells me that my rate is negative. So that's a little extra piece for this problem, the first time we've seen that happen. And so we want to use the decimal negative 0.173. And then the time, this time is in days. So that means these words here, if you'll notice, see where it says here per day, and then it says days here, those always have to match. So if they didn't match, we might have to do some conversion of some sort. Like if they said every hour, but they told us 1 day, an hour is 24, or I'm sorry, a day is 24 hours. So you might have to do that conversion. Okay, anyway, let's plop everything into our formula. So we get 100 e to the negative 0.173 times 3 power. Now, just so you don't mess that up, you either have to put the power in parentheses, but I'm just going to do it right now. 0.173 times 3 gives us a power of negative 0.219. So by doing that power first, it gives us the chance that we may not, oh, I'm sorry, I did not enter that right. I'm like, that's not right. That gives us the chance that we may not make a mistake. You know what I mean. Anyway, so that's negative 0.519. Okay, now that we do that, we can just enter the whole thing into the calculator. So 100 times e to a power of negative 0.519 gives us an answer. Now, this is grams. For the ones that are grams, I would go to 1 or 2 decimal places. I'm just going to go 1 decimal place. And you want to label what this answer means. And so, sorry, this would be milligrams. So if it says milligrams, please label it as such. So you've seen examples of things about accounts, different accounts and interest rates. You've seen some radioactive decay. You've seen some biology applications. So what I would do when you're doing the homework is, go back and try to find a problem that has a similar wording. So if you're stuck of what to do, you have those resources. So that's why you take notes. You should be, if you're going through your homework and you get to a problem, then you're stuck, try to find one that's worded very similarly, and that's a good way to approach it. So this is your 6-1B homework. So you have enough information now. You should be working on 6-1A and 6-1B. And then just check your Google Classroom for when those are due. And then Monday we will start 6-2.